Light is considered to be both a wave and a particle. And when we consider it as a wave, we need to know that it forms part of the electromagnetic spectrum. We need to know that all electromagnetic waves, including light, travel at 3 times 10 to the power of 8 meters per second. That is 300 million meters per second is the speed of light. Now, you'll remember from grade 8 that V is equal to lambda F. If the speed is 3 times 10 to the power of 8 meters per second, then if I'm given the frequency of light, any electromagnetic light, or the wavelength of any electromagnetic light, I can substitute that in for the other piece of information and work out the frequency or the wavelength respectively. If I've got nanometers, that means it's times 10 to the negative 9. So over here, I'm going to say 3 times 10 to the power of 8 is equal to 580 times 10 to the negative 9 multiplied by a frequency. And when I rearrange that, the frequency turns out to be 5,17 times 10 to the 14 hertz. You need to check that you can do that on your calculator. So this is the electromagnetic spectrum. We learned about it a little bit in grade 8. It ranges all the way from long waves that are about the size of a soccer field or something like that, size of a house, baseball, through to a full stop, cell, bacteria, molecules, atoms. So they get smaller and smaller and smaller. As the wavelength gets smaller and smaller and smaller, the frequency gets bigger and bigger and bigger. So short wavelengths have high frequencies, long wavelengths have low frequencies. No matter what though, the wavelength times the frequency, the wavelength times the frequency, the wavelength times the frequency always comes out to be 3 times 10 to the power of 8 meters per second. We start with radio waves, they are long waves. Then you've got microwaves, which are relatively shorter. You've then got TV waves, then you have got light, you've got ultraviolet, and the infrared is just kind of like heat. And then you have got X-rays, and you have got gamma rays, which are radioactive waves. As the energy, at least as the frequency of light, electromagnetic waves gets greater, so the energy also increases, and the energy is measured in a unit called electron volts or in joules, and we'll start off working in joules and then move over to electron volts at some later stage. So light undergoes refraction, we know this. It reflects and it diffracts, and this demonstrates its wave nature. All of these things are the same things that water waves do. When we investigate the photoelectric effect shortly, it's going to show us that light also has a particle nature. In other words, it comes in little packets of energy. Electromagnetic radiation, therefore, we kind of say it consists of packages of transverse waves. In other words, it has both a wave and a particle nature. The wave nature seems to predominate while it is moving through the air, and the particle nature, as it interacts with something, it seems to behave more as if it was a particle hitting a surface. Photons, the energy of a light wave is carried in packages, and those are called photons. So the particles of light are called photons. The energy of the photons can be determined by using the equation E is equal to hf. So whatever the frequency is of the wave, we multiply it by something called Planck's constant, which is on your information sheet, 6,63 times 10 to the negative 34. So what is the energy of a photon of light? So we go energy is equal to hf. H is 6,63 times 10 to the negative 34. And I then have to work out 500, I multiply that by the frequency, which I would first have to work out based on this wavelength. And we worked it out earlier on, and it was, I think it was around about 5 times 10 to the negative 14 hertz. And when you multiply that out, it wasn't exactly 5, it was 5,73 or something earlier on. And so you first get frequency from wavelength, and then you're going to be able to work out the energy, which is in joules.